Hello. Hello. Hello, Deepika.
Good afternoon, sir. Hello, sir. Are you getting my voice? Hello. क्या हो गया? सर आपको आवाज आ रही है?
हेलो.
सर आपको आवाज आ रही है? मैं उसकी बोल रही हूँ यहाँ से, लेकिन शायद आपको आवाज नहीं पहुंच रही है।
हाँ, वही तो.
अच्छा,
एक मिनट. हेलो.
सर की सर की आपकी आवाज आ रही है अभी? अच्छा, ओके
परफेक्ट.
ओके।
सॉरी, यहाँ से म्यूट था.
अच्छा ओके, ठीक है सर. सर थैंक यू सो मच फॉर ज्वाइनिंग. Because I know that this is a difficult time, but and sorry for bugging you again and again with my calls.
No problem.
Okay, sir. So we will start, sir, in 5 minutes.
Okay.
Hello, sir.
Yes.
Sir, can you share your screen?
Yes. It's D9. Okay. Just a minute. Yes. Hello.
Yes, sir. Your screen is visible to us.
Okay. Just give me a minute. Now it's visible.
Yes, sir. Yes, sir. It is visible.
Okay. So do I need to close or you want to give me?
Just, sir, just for checking purpose, I was asking you to share the. You can close, sir.
All right.
Okay. Thank you, sir. Sir, we can start the session now.
Okay.
Sir, before that, can I introduce you to the participants?
There's 2-3 minutes, not more than 1 minute.
Yes, sir. Hello, everyone. Welcome to today's session. Today, our speaker, Dr. Santosh Kumar Vishwakarma, is joining the session. So, before that, we would like to have a brief intro about him. Dr. Santosh Kumar Vishwakarma is a professor in the Department of ECE, Electrical Engineering, and leading nanoscale devices and VLSI circuits and system research group at IIT Indore from 2010 onwards. He is also a professor at Center for Advanced Electronics, Center for Futuristic Defense and Space Technology, and at Center of Rural Development and Technology at IIT Indore. He received his BSc degree in electronics from the University of Gorakhpur in 1999, MSc degree in electronics from Devi Ahilya Vishwavidyalaya Indore in 2001, the MTech degree in microelectronics from Punjab University Chandigarh in 2003, and the PhD degree in microelectronics and VLSI in ECE department from IIT Roorkee, India in 2010. From 2009 to 10, he was with the University Center Kirchner, Norway as a postdoctoral fellow under European Union Project Promotion. He has co-authored more than 200 research papers in peer-reviewed international journal and conference. He has also granted 6 sponsored projects. He is a senior member of IEEE, member of ACM, VLSI Society of India, associate member of I Institute of Nanotechnology, life member of Indian Microelectronics Society India, and member of Vigyan Bharati. Dr. Vishwakarma is the President of India Visitor Nominee for all NIT and IIST Shibipur, West Bengal, member of Academic Advisory Committee, Central Zone Semicon Future Design Initiative by Ministry of Electronics and Information Technology, Government of India, member of Task Force Electronics and Semiconductor, Government of Madhya Pradesh, Chairman of VLSI Society of India, MP Chapter, and Chairman of IEEE Circuits and Systems Society, MP Section. Dr. Vishwakarma is also a member of BIS for Wearable Electronics. He was the Dean of Student Affairs at IIT Indore from 2018 to 2021, founding faculty in charge International Relations and Placement from 2010 to 16, founding head Center of Futuristic Defense and Space Technology at IIT Indore in the year 2020 to 21, and a member of Research Park Committee, IIT Indore. He has been a recipient of prestigious German Academic Exchange Services Bilateral Exchange Fellowship in 2018 as a visiting professor at Ruhr University, Germany, and Brandenburg University of Technology, Germany. He was also a visiting scholar at Aalto University, Finland in 2016 under Indo-Finland project. So we are honored to have with you as a speaker, sir. May I now request you to start the session?
Thank you, and thank you, Deepika, and the teams, those who are organizing this beautiful session. Unfortunately, I could not travel. That's my fault. But yeah. So can you show the screen, please? Hello? Can
Yes, sir.
somebody
Yes,
help?
sir.
That's good. So next 1 hour, we'll try to see the basics of the CMOS IC design and little knowledge about the compute in memory. It's bottleneck, the problem, why we are trying to compute in memory, right? And there are 2 classes here, which you can see on the title, that is the SRAM and RRAM, that is the register RAM, okay? And the 2 why for AI chips. So all those things, but before that, I thought I should also talk about the CMOS IC design and that to the transistor level design. However, for AI chips realization and computing memory, we can go with the RTL to reduced flow also. Okay. So this is what just now you have given the introduction that, but probably for the people, those who have not explored my web presence, we are more focused in compute memory or computing memory. And nowadays AI hardware accelerators and biomedical chips, reliable, secure, trusted, and the new area we have started is the silicon photonics circuitry systems. And these are the 4 areas now we are more focused on in compute memory, or you can say computing memory for AI chips with the devices level, circuits, architectures, algorithm and applications. And hardware accelerator side, that we are trying to see the flexibility of the system as well as the performance of the specific application, whether GPU or CPU or with general purpose CPU or accelerator ASIC plus CPU, right? And then altogether the performance of the FPGA and CPU, which enhance the acceleration of the process. Okay, so there are various approaches where people are trying to intervene, and we are also trying to different techniques and method wherein our hardwares are going to be efficient architectures for the AI chips, right? So these are the few other areas where my group is focusing, and these are the some of the partners where we have engaged at different levels. And these are the few resources. Those who are there from VLSI background, they should know that it's important. Without EDA tools, I'm sorry, what is this? How come? Okay, without EDA tools, it will be very difficult to design the circuit and systems. And these are some of the famous EDA tools. Many of you might be knowing that under India's India Semiconductor Mission Program, many academic institutions are part of the Chip to Startup project, wherein the Cadence, Synopsys, and Mentor Graphics tools, and many other tools, EDA tools, academic institutions can get. And if in the other side, if there are few students or few faculty members who wishes to do the startups in the semiconductor area, then they can also apply under this EDA India Grid program. Then there are many other programs where they can find not only the EDA tool support, they can also access the free of cost the SCL in Indian Foundry, free tape out at 180 nanometer technology node. However, if any startups or even any academic institution wishes to and give the proper justification that why do we want to go with the TSMC or Global Foundries or ST Microsystems, then they can be also paid accordingly. Okay, so the India is really putting its great efforts to make our country product nation and dependent on the this semiconductor space. All right, so these are the few activities which people, those who are there, they can also think of to start the IEEE Circuit and System Society and student branch chapters, and they can also think of to start the VLSI Society of Chhattisgarh chapters. But as of now, Chhattisgarh also is a part of Madhya Pradesh chapter of the VLSI Society, where I am one of the chair. So quickly, I'm going to cover the CMOS IC design, and if there are few faculty members who wanted to enter the first time into semiconductor chip design, so this will give a complete flow that how one can start the journey and how to go ahead from the transistor level diagrams to the chip level system, that is called the CMOS to GDS2 flow. Okay. So just to start with, what is an IC? An IC is a combination of active and passive devices. And this IC is classified based on 4 categories. One is based on structure, how it looks like so monolithic, film and hybrid IC. Then based on scale of integration, I mean how many number of transistors are placed in a given silicon space at the area, right? Based on type of function, which kind of signal you are processing, whether you are fully processing the digital signal in the chip or analog signal or the mixed. Okay, so these are the 4 classification of an integrated circuits. And nowadays, what are the current product which we are seeing in semiconductor space? They're all using the MOSFETs. But now even this MOSFET is started 40 years before, but the advancement of these MOSFET devices are already been came, like FinFET and many other alternative devices. But just to start the career, or just those who are here, they can think of to start the basic understanding of the N-type metal oxide semiconductors and P-type metal oxide semiconductor field effect transistor. Okay, so this falls under FET category, field effect transistor. So the people, those who are there and those who are teaching the electron devices subjects, there you may have learned about BJT. Then you have learned about the FET. In FET, there are 2 classes, JFET and MOSFET and MESFETs. And then in JFET, you may have learned different channel, N channel, P channel, right? Enhancement, depletion. So this is how here, this is the enhancement type MOSFET, and the category is N. So this is the gate where you can see my cursor. This is the body. Then we have this drain and we have the source. And this is the 3-terminal representation. Means where body is not being shown here. So here, if you see the cross-sectional diagram, this blue color is the body. Okay. And then we have N plus, source and drain. And then the gate is the top of this red color one is the gate, which controls the flow of the current conduction mechanism from the source and drain by applying the proper potential on its gate and source. Okay, and hence the electrons which used to go from this place to this place, current conduction mechanism starts, right? And this is called the enhancement type MOSFET. So if you see here, there is a bubble sign, here there is no bubble, right? So it means when we apply the voltage between gate and source, right, positive potential, then only the current conduction starts in the case of NMOS. However, in the case of PMOS, if you apply the VGS value negative, then current conduction starts. And if you are going to make the complementary transistor with the help of these two, right, where you can see the NMOS transistor and PMOS transistor. Here you can see the 4-terminal representation, that is the gate, source, body, and drain. And here source, gate, body, and drain. Okay, so in the case of PMOS transistor, the source is supposed to be tied the highest potential, and in the case of NMOS transistor, the source is supposed to tie the negative potential. Okay, then only the current mechanism starts. So in the previous slide, you may have seen that we have biased the transistor with the input gate voltage and output drain voltage, and hence with the potential difference between drain and source, the current conduction starts. And you can see the ID is flowing from drain to source, and the carriers are going from source to drain. And hence, if you see this diagram where the on y-axis ID is there, on x-axis VGS is there, right? So if you keep increasing the VGS value, right, at a certain threshold voltage, the current starts, all right? And this is called the relation between ID and VG. VGS is the input voltage and ID is the output current. So this is called the transfer characteristics. And this voltage is called the threshold voltage. Okay. So this is the y-axis in the linear scale. Okay. However, if you plot the log scale, even here, what we are seeing here in the linear scale, the current is 0 and when the VGS is 0. But in the log scale, you will find small amount of current, and that is in the range of picoampere or something. What it says that even if the gate voltage is 0, means the transistor is off, the current starts. Okay, but that amount is very, very small, and that is called the subthreshold leakage current. Similarly, if you see the here you have the drain current, and here you have the VDS. Okay, sorry, here is the VDS, and this is the drain current. Okay, so here at different value of VGS, you are seeing the different amount of drain current. Okay, this is so the output current and output voltage called the output characteristics. And here you have the linear regions of operation for all value of VGS, and after that you have the constant, or you can say saturation region. So you have saturation region, linear region, and cutoff region. So cutoff region means when the current is 0 for irrespective of the VDS values. Right, so when the VGS is less than 0, the current is not supposed to be flow. All right, so this is the fundamental MOS characteristic. That too for the NMOS transistor. Similarly, you can also figure out the characteristics of the PMOS, and if you are making a combination of the NMOS devices and PMOS devices, so this is called the CMOS. That is a complementary metal oxide semiconductor field effect transistor. Why complementary? Means with the combination of the inputs, either NMOS will turn on or the PMOS network will turn on to verify this output logic. Okay, and this is once again here you can see this is the VTC curve called the voltage transfer characteristics curve, where the input voltage and the output voltage we have drawn the relation. So that you can see there are 5 regions of operation: the region number A, region number B, region number C, region number D, region number E. Okay, and hence you can calculate the noise margin low and noise margin high, and this is the switching voltage. Okay, or you can say switching threshold voltage sometime. Okay, or you can say sometimes threshold characteristic voltage. And these are the condition of the MOS transistor in the region number A, B, C, D, E. And depending upon these condition of the NMOS, cutoff and linear, saturation linear, right, the current conduction starts, and hence you can calculate the VIL value and VIH value, and hence with respect to input voltage low, you are getting the output voltage high, which you can see on the y-axis. Similarly, the input voltage high, you are getting the output voltage low on the y-axis, which is shown over here, right? So when you try to calculate the slope over here, okay, dV output divided by dV input, the slope of the output voltage versus input voltage, okay, which is you can say -1, and then you can consider and calculate the VIL value and VIH theoretically, and as per the formula of the noise margin low, noise margin high, you can calculate the value of low and high noise margins of the CMOS logic circuit. So the beauty of the CMOS logic circuit is you can get the VOH. This VOH value is supposed to VDD, and this VOL value is supposed to as small as possible, and in this case it is supposed to be 0. So you can get the larger value of NML and NMH. Okay. Now, as far as the technology is concerned, CMOS processes are very simple, where you have a p-type substrate. You need to create the n-type well. In n-type well, you can make the PMOS transistor. Here you can see P plus P plus, and in n well you can make n plus, that is NMOS transistor. Okay, and this is called the standard CMOS process technology, where NMOS and PMOS used to be fabricated on the same well, same substrate. Okay, and coming to the transistor level, or you can say the layout level view, here you can see if you wish to make the CMOS inverter, right? So this is the ground line, this is the highest power supply, that is called the colored with the blue color. Okay, and this red color is the polysilicon, and this green color is the diffusion, and the yellow color is the P well. Okay, sorry, N well. And then this is the NMOS, this is the PMOS. Okay, so PMOS used to be created in the N well. And if you see from the top, right, so you can find like this characteristic, that you have the N well, which is the yellow color line, and then you have the green color diffusion line, where you are going to make the PMOS transistor, and here you are making the NMOS transistor. And okay, and these are the contact curves which has been shown, and this red color is the polysilicon line. Okay, which you can say, and then you have also seen that the field oxide, and field oxide used to isolate one device to the other device, which is thicker as compared to this thin oxide, which is the gate insulator thickness. Okay, so here between the red and white there is a called the oxide thickness, but here there is a field oxide which used to provide isolation from this whole device to the nearby device on one same substrate. Okay. Now coming to the circuit side, because our plan is to take you the journey towards how you can design the semiconductor chips that will allow our digital. So we need to have the PDK. Without process design kit, that is called sometime technology file plus Spice Verilog file. Okay, this is a combination of this, and this and technology file used to have the design rule definition. What is design rule definition? So design rule definition used to be given by these foundries, any foundries, IBM, Intel, whatever required is. You cannot design anything whatever you wish, so we have to follow the minimum separation, minimum width, and so on and so forth of the one line to the other line. Okay, and the device definition, the parasitics also used to be defined, that if you are going to place one line to the nearby, then how much parasitic is supposed to be followed, right? So altogether you can create the schematic, then the DRC, then the LVS. DRC stand for the design rule check. So the software, these softwares, Cadence, Synopsys, whatever software you are working on, even open source also software you can think of, but all those places where we need the foundries defined PDK, okay, and the design rules, and we are bound to follow these rules. If you not follow, your design will not be the correct, and your foundry will not accept your design. So coming to the India ecosystem, Indian Semiconductor Mission Systems, SCL is the Indian foundry which used to offer 180 nanometer PDK, which is sufficient enough for designing and developing the chips, test the chips in India itself. So I recommend that those who are not availing the SCL PDK, please be in touch with the CDAC Bangalore. Now CDAC Bangalore is the Chip India Center in the country, and everybody, students, startups, MSMEs, and big people, they can approach to the CDAC Bangalore, and then they will issue the PDK. And with the help of those PDK, if you are designing, you can send your design to the CDAC Bangalore once again, and then after checking your design at different steps, they will send your design to the SCL Chandigarh for the fabrication of the chip, and then the chip will send back to you for testing. If you wish to test the chip, you can also do in the SCL Chandigarh once again go. Okay, so this foundry is really established in 1984 or something, much before I should say, where the Taiwan also entered into the semiconductor fabrication business. But this was primarily for the ISRO and the DRDO chips, very strategic for the space application. and defense applications. Even our Chandrayaan, this right, recent Chandrayaan, right, Land Rover or something, the many processors has been designed using SCL180 only. Lots of memory chips has been developed on these foundries. So these are the worldwide various fabs where you can see like eFabless is also once again a kind of free open source softwares they used to ask you to simulate and design and develop, and with a very nominal charge, not more than 20,000 rupees, you can send design on their own foundries. Okay. Skywater, this is the American foundries. They also offer the free of cost sometimes settles with the Google. Okay, and Europractice is very important slide where if you click this, then you will find what are the PDKs available by the different foundries. Okay, for example, IHP Germany, STM Microsystems, TSMC, United Microelectronics, all big foundries detail you can find here. And you can also find the pricing for that. I mean, for 1 millimeter cross 1 millimeter, what is the price, and which month the if you are submitting your design, your design will be accepted. Okay, so Europractice, if you want, you can note down europractice.ic.com. This is a very important link where you can find huge number of information. As of now, things are clear. Can somebody help me from the other side? I am audible or not? Hello, Deepika or anyone?
Hello. Yes, sir. All going well. Please
Okay.
continue. Yeah.
So what I was suggesting that if any professors wishes to do, please follow this Europractice site where you can find all relevant PDK. What is happening in the country that people are neither using this SCL PDK nor industry standard PDK either came from the TSMC or IHP or Global Foundries or STM Microsystem, United Microelectronics Corporation. Anyway, so people are always trying to use this generic PDK. Generic PDK don't use, otherwise, I mean, your design will not be accepted after certain years. So please sign the NDA with the help of these foundries, either SCL or TSMC or IHP or any other foundries. Once is a very simple process. You can find the NDA signing documents on this Europractice. Okay, on the services, if you click services here, where my circle is there, our technology, you will find one email where you have to just send that virtual asic@imec.ac.in, Europractice or something, and there you just fill that form that why do we need, which technology do we need. For example, TSMC you have 180 sorry 130, 90, 65, 22 and so on and so forth. Okay, so which technology is of your use, you have to decide, and you have to just fill some NDA document, and as a group leader of your group or your dean R&D can sign, and you can start using those tools. Now, if in your research group or even your institutes, if 4 students are using, 5 students are using, so even everybody's name should be there before while sending the NDA, because everybody is supposed to bound and follow the policy of these foundries. But it's a very simple process. But please do, because what is happening in the country, many people don't follow signing the NDA and just taking the the PDK from generic PDK or here and there and just using. Now, what I talked in the very beginning, that this is the schematic to GDS flow. So what is GDS is the format, okay, where finally you are sending your design from the circuit level schematic to the taping out the chip. Okay, so all those steps like pre-out layout simulation, circuit design manual, DRC check, layout versus schematic, parasitics, post layout, and if every time if you are finding bit difficulty and you are not meeting the requirement, then you have to, and if your simulation failed or checking failed, then once again you have to redesign and follow the same thing. So it's nothing to worry. I mean, what I'm trying to say is that whatever circuit you want to verify functionally or something, or try to meet the specification, you have to follow these steps till the taping out the chip. Okay. And Then the other approach which I talked about, the RTL to GDS2, where you are entering your design meeting either Verilog or System Verilog or VHDL, and then you follow synthesis. And so primarily for all digital blocks, this steps we have to follow. Okay, this system. But at the transistor level also you can make the digital blocks, not a big deal. But here also, if you follow and we had described the behavior of the circuits using this scriptive language, then ultimately also you are going to make the physical layout or something after this, and then finally you can tap out the chips. So in both the steps, ultimately you are reaching out to the GDS2. GDS2 is the format which industry or foundry accept. So I was just talking about the schematic and layout view of the CMOS inverter, which has been designed at the Indian foundry called 180 nanometer. So here you can see the NMOS. What is this? Some message came. Oh, sharing computer audio. What is this? Do you want to include your computer audio while you are sharing? Can somebody cut? What is this? Okay, I'm not able to. Okay, just a minute. Cursor is not working. Anyway, so can you see the screen, please? Somebody confirm. Hello.
Yeah, yes, sir.
So I am facing some problem. This somehow this block comes. Okay.
But sir,
Okay, but now can you see once again?
yes, sir. Yes, sir. It's clear.
Right. So the people, those who wishes to enter into this analog transistor level design, which is called the full custom design. Full custom design means every standard cells, either inverter, NAND, NAR, every basic cell, you are designing yourself. Okay, you are not taking any standard cell which is readily available in the library. Okay, so what does it mean? For example, if this is the CMOS inverter where NMOS is there and PMOS is there, you are trying to meet the best of best design of this inverter. Okay, by putting and changing the LWL, transistor sizing, and so on and so forth. And this is how you are making the standard cell of using this kind of layout diagram. Okay, of this. So this is the NMOS, this is the PMOS, this is the width, this is the length of the polysilicon, this is the ground line, this is the VDD line, and these are the contact cards, right? So everything, and then you are putting this input A, and you are getting the output A bar, which you have taken from this side, and input is the polysilicon. So here I'm trying to explain is that the CMOS schematic and layout has been shown of the inverter, and these are the functional verification of the input and output. Okay, similarly, if you wish, you can make the stick diagram of the NAND gate. So you people may have learned. If not, then I'm explaining you that this diagram is the 2-input NAND gate. How NAND gate? So the philosophy is very simple. These are called the pull down network, and these are called the pull up network. So the job of the pull down network is down the logics. So whatever you are storing over here in output node, it will try to down the logic. For example, if 1 is stored over here, so if you are applying the appropriate input, so both the transistor will work accordingly so that it converts from 1 to 0. Okay, and similarly the job of the pull up network is to make this output up. Means if it was stored 0, it will count the logic from 0 to 1. So through this voltage will appear over here if this transistor will turn. So in the worst case, either this transistor or this PMOS transistor will make this output high. Similarly, in worst case, both the transistor is supposed to be turned on. And this is the another form, say different form of making this schematic in different fashion, nothing special. And then with the help of a stick diagram, you can make the layout. Now here is simply putting the color diagram. Here the poly A line, the B line, then the ground line, then green is diffusion line, yellow is the p-type transistor. And since these two transistors are parallel, so the rule says very simple. If one input goes highest power supply, the other input will go down. The other output will, diffusion line will go up. So if one goes up, down, up. Okay, so this is the PMOS transistors are setting. However, if the transistors are placed in series and if one input goes down, so in between no need to take anything, the extreme right will go out. Okay, here we are talking about A and B, that is only two input. But assume that if there are three inputs, then what will happen? We have to draw another polyline, right? So one input, one extreme diffusion will go ground, no input between, and then the extreme will go out, right? Similarly over here, if this terminal goes up, down, and then up, and then down, okay, and this down is supposed to go up and make as output. So if the transistors are placed in parallel, so if one terminal goes highest power supply, other was down, ups and down. Okay, and if the transistors are placed in series, nothing to worry. Take left one down and rest we connect. So here is the diffusion merged. So all the points, all the contacts are merged over here. Okay. And why do we need to merging diffusion? Because of the less parasitic, or you can say the least parasitic. This is the art of the layout design engineers. That how we are going to make the layout so that it can offer the least parasitics. And why do we need least parasitics? So parasitic means the R and C, because these are the layer, these are the wires. And each wire, if you run parallel wires, they will offer the capacitance. And if you have more capacitance, it will offer more delay. So the layout designers are supposed to make your layout very smartly set so that it should offer the less parasitics. So if you wish to work on the tool, you are supposed to design and place the wire, transistor, and so on and so forth. You can make the layout. Similarly, just now this is the FDP. So in faculty development program, oftenly we do the hands-on session, but today I'm not able to do. But here, if you are supposed to, this is the cadence environment where this is called the Virtuoso schematic editor, okay, where you are supposed to place the transistors, define its length and width, define the wires by shortcut. Just if you press wire will appear. Otherwise, you can go here, drag and docs box, and you can make, okay. And then finally, you can find out the characteristics of the drain current versus gate voltage. Okay, so these are the different characteristics you can obtain using the SCL Virtuoso 180 nanometer PDK. Okay, here is just what I'm trying to demonstrate is that how one can make the cadence environment, these logics, and these is the one inverter, and this is the symbol of one inverter, which says only input, output, highest power supply, and ground supply. Now this is the instance which we have created for the CMOS inverter, and this CMOS inverter can be reused, and hence in VLSI design people prefer that one standard cell is supposed to be reused, not necessarily that every time we have to redesign. Okay, and then now you have to create a symbol. Okay, and then you have to give it test bench. So test benches are the how the input pulse should be there, right? What should be the V1, that is the, and then what should be the VSS ground line. And then for each word line, I mean high voltage and low voltage and input voltage pulse, if you define it, it means this test bench will be given, and accordingly you can get the output. Now here if you see different analysis you can do, transient analysis, DC analysis, AC analysis, these are the type of analysis which, let us say here we have chosen the transient analysis, means with the time how it looks like. So let us say you have given the stop time of this, if you click this, and then finally, since these are the only MOS transistor, okay, so we have to define its model. Okay, so model stands for that what are the models, which are the foundries. For example, here 180 nanometer SCL foundry, okay, the .lib file. So .lib file is the standard file. Okay, so if you put it to the proper wherever we have stored, then it means that now you have introduced the model file with the name SCL180. Okay, TS. And if you browse, then you will find what kind of characteristics you wish, either typical, or slow, or fast, slow, and so on and so forth. Okay, so you have to select the process corners. So what is happening and why do we need to select the various process corners? Okay, so your design should be checked in all the process corners. So when I'm saying process corner means the temperature, voltage, right, PVT variation. Okay, so process voltage, what are the processes, means when the transistor is length is, let us say you are working on what technology node 180. So the process can be either 179 or 178, and then our length can be 182. So your transistor should give the best performance for all processes. Okay. And then accordingly, you can find out the appropriate. Here you can see you have found the bump over here at each node, and this is because of you have not connected the appropriate here the output characteristics for the next stage, right? So if you put the output capacitance over here, probably you will not find the bumps over here. Okay. And each technology and the finding out what should be the load capacitance over here, right? The load capacitance will be the sum of interconnect capacitance, the output capacitance of the inverter, and the input capacitors of, the capacitors at the input stage of the next inverter. Okay, so all together gives the C load. So C load calculation is a tedious process, and this C load calculation can be calculated from the various PDK parameters of the technology file. Okay, and the length and width and so on and so forth. So generally people don't do, but we should do. If you will do this, and then if you put the appropriate capacitance on the load, you will find the very nice functional verified characteristics of the studied logics. Now this is the VTC plot which just now I talked about, that this is the input voltage at 1.8 volt. Here is the output voltage at 1.8 volt, and this is the switching threshold voltage, that is 0.9 volt. Okay, close to 0.9 is the switching threshold, half of the power supply. So likewise, you can calculate the propagation delay, and just to understand you people that how to calculate the propagation delay. So when the output node is fluctuating low to high or high to low, okay, so here TPLH, low to high. So this is the red color button is input pulse, and the green color is the output pulse. So when the output pulse is going from low to high, okay, so here is the definition is 50%. So 50% means if this is the 1.8 volt, so 0 to 1.8 volt, 50% is 0.9 volt. So wherever 0.9 is here volt, and similarly 0.9 volt for the lower graph is here somehow, right? So difference between this 50% to this 50%, that is 0.9 volt here, 0.9 volt here, called the tau P LH, that is 12 picosecond, for example, in this case. Similarly, when the output node is going from high to low, okay, and this is the input 50% here, 50% here, you can calculate and find out 17 picoseconds. So you see here, there's a difference. Tau P LH is 12 picosecond and tau P HL is 17. Why we have got the two different rising and falling edges delay? Because of the various capacitances and the length and width of the transistor, and worst case situation of the NMOS and PMOSs. Okay, so and the average of these two will give you the overall propagation delay, that is called the average propagation. So with the help of open calculator also you can do light. So noise margin can also be, just now we talked about that how to calculate the noise margin. So this is the VTC curve, right? And then with the help of VTC curve you can also calculate different VIL value, VIH. Theoretically I was talking what is VIL and VIH, and once you know the value of VIL and VIH, you can figure out the calculation of the noise margin high, noise margin low by subtracting VDD minus VIH will give you noise margin high, and VIL minus VOL, that is 0, equals to give you noise margin low. Okay, so all those calculations you can do here. Now it's our job to calculate is the power dissipation. For example, how much power is being dissipated by the studied circuit. All right. So with the help of power analysis tool, if you go, you can calculate that how transient analysis power is being consumed. So with the help of power, you can easily calculate the dynamic power, static power, and now it's job to make the layout of our selected files. So now you have to launch the layout Excel, and then you can make the layout of just now we talked about, and with the help of Calibre. Now the Calibre is another tool of the other company EDA, okay, where you have to run, and then with the, if in case you are finding some error, then you have to resolve and you have to run once again. And if there is a correlation between layout versus schematic correct, then you will find here the correct kind of symbols, and you can also find over here if it is correct. So layout and schematic need to be verified and called the layout versus schematic. And now it's job to find out the parasitics, means what are the parasitics, what are the resistance and capacitance offered at various electrode, right? So with the help of here Calibre tool, once again with the Siemens EDA tools, that its name was Mentagraphics. Okay, so in Siemens you have to check its parasitics. So if you follow these parasitic checks, right, and if you extract all the parasitics and if you compare, so with the help of the Calibre tool of the inverter, right, CMOS inverter and the layout simulation, if you do, you will find various parasitics R and C at each node of the circuits. So there you'll find, if you see here before parasitics means the pre-layout simulation and post-layout simulation. Okay, so you will find the mismatch, at least delay here we have shown, but similarly in the power, in the many things you will find difference. But ultimately the parasitics oftenly decides the performance of the circuit, or you can say delay of the circuits. Okay, because the resistance and capacitance comes in the picture. So that is what the post layout simulation is very, very important. Here you can see the post layout simulation. Okay. And then finally, whatever logic you have, that is inverter logic, you have to give the IO padding. So IO padding means what are the IOs has been defined by the various metal lines and so on and so forth. So here if you see, here the simple logic sitting with the input, output, VCC and VDD. But these are the input output of IOs, okay, and which are supposed to be placed to the actual input so that externally this can be connected. And these IO pads used to be given by the foundry, number of metal lines, okay. And now finally you have to export the GDS2 file from the, which means that you are translational, the complete from the special design to the GDS2 format. And finally your inverter 2 name, let us say inverter 2 GDS file you are getting. And now this file, the description of this file, only the foundry learn and accept. Once you send this file, GDS2 file to the foundry, they will fabricate your chips looks like this. And these are the package chips. Package means these are the wafers and these are the dies. And these dies used to have various bond wires. And then you have to package either ceramic or dual inline package or something. And finally, you can put the legs. And these legs we have seen into the labs and actual product, which are mounted onto the PCB. So these are called the package chip. Right? So these are the small hands-on. We should not say hands-on because I have not asked you to do along with me. But this is how we used to process the complete flow. This was the flow called the CMOS to GDS2 flow. Similar flow we can follow in from RTL to GDS flow. There we have to describe the behavior of the logic using with the help of RTL. Okay, so RTL means the Verilog or system Verilog or VHDL language base. Okay, and then there are also these tools can be useful, or maybe you can go with FPGA level, but FPGA level will not means we have to go beyond that physical layout, and then we have to follow these industry standard tools. Okay, Deepika, how much time do I have now? Hello.
Sir, till 5 o'clock, you can continue half an hour.
Okay, all right. So quickly, not more than 10 minutes, I will spend on this. As of now, what we have learned how to make the CMOS inverter, IO padding, parasitics, and then finally how to get the GDS2 format of that. Okay, using SCL 180 nanometer technology. Slowly, we are moving towards computing memory. So you all know that the arena has been changed where huge data we are running in and around, right? So every day, either the car and anything, whatever you can think of, almost everything looks like a data center, right? Full with the sensors, full with the internet, right? Everything is like that only. Okay. So autonomous car, so almost all those things which is internet driven are data intensive applications, right? We can have two options. The first option can be the either cloud. The second option can be the edge. Okay. So the problem with the Von Neumann architecture, which you can see here, was like that there was one processor, okay, and then there was one memory units, right? And every time you have to go with the data movements, right, from processor to the memory, depending upon the control lines or control signals. Okay, so if we can do both the things and the same, I mean the if you can process the data in the memory itself, right? So the Von Neumann problem which was there, which is traditionally architecture in between the of the CPU, can be avoided. So it reduces the data movements. At the same time, it also reduces the latency. So latency means, because whatever in the cloud we used to go, right, if the sensor comes sense the data, okay, and if you compute and send back data to the cloud, so the cloud is a remotely located big servers. So but when data science goes and come, it will have create some latency. So however, if there is no movements and if you have your chip is very competent enough, right, either traditional memory or non-volatile memories, right, so this will have a reduced latency. And then now algorithm level also people are trying to design the efficient resource utilization. So what are the advantages? The advantage can be the faster data processing, low power consumption, even low latency and high throughput, and even with the less internet, right, you can access the data. Okay. So power is really consumed very less, right, as compared to the traditional computing resources. Okay. So this is the framework of computing memory, where you have to have a bit cell. Okay. So here if you see about this, so the circuit level bit cell, and the bit cell level also you have to have the device level. Okay, whether SRAM or RAM or PCRAM or whatnot. Now, with the help of this bit cell and peripheral circuit block, okay, which you can perform some operation. So whether you wish to perform the digital computing memory, so digital computing memory or mixed mode. So digital computing memory means you are not using any sort of analog in nature. Okay. To digital converters or digital converters. So here, for example, the digital SRAM based CAM. So where the Boolean logics can be performed and NAND NOR operation. Then the content addressable memory can also be binary CAM and ternary CAM can be performed. The mixed signal means a single bit or multi bits, right? Where you are controlling the dot product, ternary product, and Hamming distance, MAC and side, so on. And if you want to go from the function to the application, so we have to either see whether you are planning to use these weights, because at every cell you are supposed to store the weight, and from where this weight comes from the DRAM, which are supposed to be in the processor. Okay, so and each this image size, right, is supposed to either convolute or filter and so on and so forth. Then you can say whether you are able to do the matrix multiplication. But ultimately it's a matrix multiplication. Okay, and all those things are happening at the cell level. So these are the simple memory array architecture, which you may have all known that, right? That how things evolve. So I will not say much time, but here once again, you are seeing that these are the word lines, okay? Dotted color line, word lines. Okay, depending upon these word lines, let us say if a number of rows and columns are there, so that should be the size of the memory array, right? So for example, here if you have m rows and n columns, so the size of the memory would be m cross n. All right. And many of you may have learned about the various SRAM memories which has been designed by various foundries. So 6 transistor SRAM cell is very popular, where you can see two inverters are cross coupled. So when I'm saying cross coupled means the output of first inverter goes and act as the input of the other one. Similarly, the output of the second inverter goes and act as the input of the first inverter. And then you have the access transistor Q here and here. And then you have the bit line and bit line bar. And then with the help of their word line, right, you are activating these access transistors, and hence depending upon the voltage line which you are applying with the pre-charged circuits over here, okay, the bit line and bit by line bar is supposed to be given, and hence either is a reading or writing operation used to be there. So as compared to DRAM, where only one transistors and one capacitors are needed, here the packing density is very, very high, okay, but it's very, very fast. So these are the various topologies of having memory cell, SRAM, say 8 transistor, 9 transistor, 10 transistor, many transistors has been evolved, right? But traditionally, without compute memory, 6 transistor and 80 read decoupled transistors are very, very popular, okay? But in compute and memory, probably we have to evolve different cell architectures, okay? Who can gives the, once again, these are the basic operation of the read, write and hold operation of 6 transistor SRAM cell, okay, and how to keep the sizing of the N1 transistor, N2, 3 and 4 and so on, so that it properly you can read and write the transistor, okay. So these things we have to keep, and hence accordingly there are various pre-charge circuits called the which used to be bit line, we have to make the bit line high before the reads, okay, and then we have to have the row decoders, column decoders, as well as the row decoders, right? Depending upon the size of this, we have to also make sense amplifier. Sense amplifier, once again, the differences sense amplifier. There are also the current sense or voltage sense or hybrid sense. There are various classes and advantage of each other, okay, and these are the SRAM layout, okay. So what is the learning here, that in case now I was talking about the DRAM where only one transistor and one capacitor is supposed to be, okay, and this is how one can understand the read and write operation. Coming to the another memory, right, which is called the RAM, that is the resistive RAM. So generally what happens, that the resistance varies, resistance changes of the resistive RAM, okay, which is shown over here. So if you have proper charge, the flux generated and the resistance value changes. So this gentleman who was a professor in University of California, right, Dr. Leon Chum, he was the first person in 1970 who has given this concept of is a missing element. And finally now this resistive RAM is very, very popular among the AI chips, because we have to store huge number of data, okay. And you can find the various open source RM models with the Technion Israel, RWH in Germany, Stanford and University of Southampton, and many foundries like GF Global Foundries, IHP Germany and IMEC Belgium. They have their standard MRAM model files, and if you have the standard model files, you can make the circuit and systems, okay. So here you can see that over a period of years, that how Samsung reported RM in 2004, 2007 Infineon and Samsung, 2008 HP, then 2013 14 SanDisk, and then Micron. 2020 TSMC announced the production of RM at 40 nanometer and 22 nanometer technology node. 21 Webbit Nano Skywater announced, and now many more have evolved, and Global Foundries already acquired the Renesas non-volatile resistive RAMs, okay, and technology to proliferate IoT and 5G applications. So this device is also very important. It is a very simple device that compatible to the CMOS, okay. So it means we have a top electrode and bottom electrode and metal, okay. Now by applying the voltage, right, this resistance varies. So it's a very simple device which is very much suited and follow the CMOS process. So here you can see that there are two methods of classifying the oxide RAM and the conductive bridge RAM, okay. And here if you see, here you see two mechanisms, switching mechanism. One is a unipolar and the other one is a bipolar. So in the unipolar, right, unipolar device, if you see here, unipolar device and bipolar device. So in the unipolar device, you have to keep plus on both the devices, where these are the filaments, okay. And then LRS stand for low resistance switching path, okay, and HRS stand for high resistance switching path, okay. And here bipolar devices mean both the polarity you have to give. For LRS you have to give positive, for HRS states you have to give the negative. So here you can understand the resistance increases or decreases depending upon the applied potential. This also you can understand here in the bottom diagram, the unipolar device, that voltage and current. So you have to change something about set. After certain voltage of set, you current maximum command of current used to flow, and then you have to reset, right? So the set and reset phenomena used to happen with a positive voltage. However, in the bipolar device, the set operation happen in the positive voltage and the reset operation happen in the negative voltage. The same has been shown, okay? Set and reset called the bipolar. So both people used to follow, okay? So the low resistance path and high resistance path. This is the RWTH Akin model, where you can easily download the PTK of this RAM file and you can make the circuits. Now coming back once again, the in-compute memory using 6 transistor SRAM cell. So here the learning is that we have designed this 6 transistor SRAM cell, okay, using standard CMOS technology file, okay. And then you have made the various rows and column and control logics. So the basic operation was supposed to be performed very successfully with the help of this AND and NOR, and finally XNOR and XOR operation. And these are the different other basic ALUs which has been performed. But it was a difficulty to calculate the power, and it was also difficulty to figure out the complex logic functions, okay. So what happens that since we were facing this problem, so the workers has proposed a 10 transistor SRAM cell, okay, which was very good to improve the stability and low latency, variety of read operation can perform. And it has also the feature of decoupling the read and writing, which removes the read disturbance, okay, and large variety of computation and efficient of BNN and CNN also. BNN stands for the binary neural networks, and convolutional network also you can perform. So here you can see that this is the type 1 operation, and this is the type 2 operation, basic ALU operation, advanced operation. So successfully with the help of this 10 transistor SRAM cell, it was supposed to be performed. And cell is being shown over here, who's the read, write, and all those, these are the control signals which was supposed to be given so that it can perform the various operation which you can see here. And then you can perform the dot operation, right? And then lately you can perform the various operation, and you can figure out the throughput and latency of different these logic gates performance. And here you can see the reconfigurable incomplete memory using, right? So here the sorting and searching operation has been performed, that how you can figure out the zeros and ones in the stored memory banks, okay. So this also you can see that how has been performed. And finally at the algorithm level, right, so this is the purely software level work where you have taken the scalable hierarchical convolutional model, okay, And if you see here, we have taken the 3 data sets. One is the MNIST data sets, which is 10,000 samples of the hand digits from 0 to 9. And the cipher 10 and cipher 100. These are the classes, okay? And then this is the algorithm which requires this much accuracy for the cipher 100, and here cipher 10, 16 classes were there, okay? So in the binary neural network, 48 million operations are supposed to be, but even SHA require only 35 million operation, which is less operation. So you are performing the less number of operation with the same algorithms, okay? So it means your hardware is very, very efficient, all right? And then we have also demonstrated the algorithms on the PinkJet1 board, okay, with the help of the Purdue and Briggs. Now coming to the other alternate device, which I was talking about, the RRAM. So with the help of RRAM, if you consider, but before RRAM, you have to go back and fix the value of RHS and LHS value, low states and high state value, and then you can consider that if resistance value is this much ohm, right? So you will consider high or low digital, right? Similarly, you have to perform various combination, and you confirm the NOR, NAND, and right, to input NAND gate, NOR gate, and so on. So what exactly learning here is, if you have the resistive network over here, right, and if you are having the V1 input and G1, then you can current, you can calculate, and the combination of plus I1 plus I2 gives you this. So you can perform the CNN network, you can say, you can map the values, right? So here is the weight. Here is the weight are going to be stored on these RRAMs, okay? These weights are coming from these word lines, okay? And then altogether the current gives you and compare it, and then finally you are mapping. So basically you are going to give the different weights through the various rows, right? And from where these weights come? Weight come from the trained model, which are supposed to be showed into the DRAM previously, okay? This is called the mapping of the neural network in the in-memory computing, okay? So weights will be trained, weight will come from the CNN algorithms, and for the particular set of images, data sets, and so on and so forth, those weights are going to be stored in these RRAMs, okay? And then depending upon the weights, these transistors are supposed to be on, and finally you can calculate this the V1 into G1 plus V2 into, that is the matrix multiplication, okay? So this is how one can learn that how matrix multiplication used to be happen. And then once you, so one neuron means one MAC operation plus activation function. And similarly, if you do the coding, you can find out various weights values of weights, okay? And those weight value you can store in the memory, and then that can be act as a AI accelerators. And these are the some of the pics of our previous students, some of ongoing. So I would like to acknowledge all my group members and the collaborators in the funding resources, and they have done all wonderful work in this space last many years. So that's done from my side. And then if anyone has any concern, then we can take it.
So anybody has any question?
Thank you, sir. Thank you for this wonderful session.
Yeah, thank you.
Thank you, sir.
Sir, I wanted to present the moment of appreciation to you by myself, but yes, unfortunately, you are not here.
You can show me.
No, but my scholar Chanchal will be visiting VLSI Design soon, so she will be handing over to you in VLSI
वहां
Design.
मत देना, वहां बहुत सामान रहेगा.
अरे नहीं सर, आप और तो
वहाँ
कोई
से-
तरीका नहीं है सर आपसे मिलने का.
हाँ, अगर वो आएंगे तो ले लेंगे, पर ज्यादा बड़ा हो तो एकदम मत भिजवाना आप.
नहीं तो छोटा ही है. आप
छोटा
उसको
है तो
और
ठीक है,
बैग
अदरवाइज
तो बैग देंगे तो बैग में रख के आप आराम से उसको कैरी कर सकते हैं.
हाँ, क्योंकि वहाँ ऑलरेडी सामान बहुत हो जाते हैं आते जाते में.
हाँ
That is my submission, है ना?
Thank you so much sir for taking out your
Thank you.
time for this session.
Right.
Thank you sir. Okay.
तो अगला मीटिंग कब है दीपिका? अभी कोई मीटिंग
सर अभी DSRC में भी सोच रहे हैं जनवरी में करने का, सो आई विल कॉल यू इन जनवरी।
चलिए
थैंक यू
ओके
थैंक यू
बाय
सर, थैंक यू सर।